Okay, we're going to start the rounds of spotlights. We're going to start with Wei Su, who's going to be presenting his work on a differential equation for modeling Nesterov's gradient acceleration method, theory and insight.
Hello, my name is Wei Su, and I'm going to talk about an extensively used technique in modern optimization, Nesterov's accelerated gradient descent, proposed 3 decades ago. This scheme has an optimal 1/k² convergence rate for convex functions with Lipschitz gradients. This speed up is widely attributed to the introduction of a momentum term, but no physical or geometrical intuition has been provided yet. For example, why should the momentum coefficient k-1/k+2 be that specifically? Our work starts with letting the step size s approach 0 and thus obtains a differential equation to partially illuminate these mysteries. These 3 plots are the trajectories of Nesterov's scheme, minimizing a 2-dimensional quadratic function. As the step size approaches 0, the trajectories converge to a smooth curve. This curve is governed by this ODE, which consists of 3 terms: acceleration, speed, and the driving force. And this ODE is non-trivial in the sense that it's singular at time 0. Now let's compare Nesterov's ODE and the gradient descent ODE. Here, L is the Lipschitz constant of gradient f. These 2 plots reveal 2 interesting points. First, the stable step size for numerically integrating Nesterov's ODE is of order 1/√L, whereas it is 1/L for gradient descent ODE. So conceivably, Nesterov's ODE is more numerically stable, robust for numerical integration when L is large. Second, Nesterov's ODE moves √s at each iteration along the curve in time t, while gradient descent moves s. So as a result, Nesterov's scheme moves faster near the curve in time t when s is small. Later in the post session, this ODE will also suggest some variants and improvements for Nesterov's scheme. Thank you.
Thank you very much. Up next, we're going to be presenting Srikumar. He's going to be talking about learning distributed representations for structure output prediction.
Hey, good morning. This is joint work with Chris Manning at Stanford. And the question we are exploring in this paper is whether structured output should really be treated as discrete objects. So I'm going to give you the general philosophy of this paper. A very neat idea that we have seen is the use of distributed representations for inputs. A manifestation of this idea is to, for example, if you have words, represent them by real-valued vectors. And the reason this is a reasonable thing to do is words are really not discrete units of meaning. Some words are more similar to each other than others. And the vectors can capture this kind of similarities. Now, in this paper, we are thinking about structured output prediction, which is a common setting in many NLP, computer vision kind of problems, where the output is a labeled graph. The thing to note, the observation that we make in the paper is that these labeled graphs, actually the labels that compose these labeled graphs, are also not discrete units of meaning. There are clear similarities between some labels, and our current models do not exploit them. I have a toy example on the slide here of part of speech tagging, and you don't have to necessarily understand the details of it. Come talk to me during the poster. These 2 sequences here, if you look at it carefully, are very different. But in fact, if you understand the semantics of the labels here, all the highlighted labels are transitions from adjectives to nouns. They are just minor variations. And adjectives and all the JJs are adjectives, and they form a cluster that's closer to each other than all the other labels, for example. But as I said, despite clear similarities between outputs, standard models do not take advantage of these similarities, so that's the starting point of this paper. We propose a method which models labels, which are, again, as I said, not atomic units of meaning. We model labels as dense, small, real-valued vectors. We propose an operator that can combine these labels to form larger graphs. The cool thing about this operation is that it also gives us the definition for feature vectors for factors, and now we can use all the fun stuff that we know about factor graphs and such as inference. Another neat observation is that if we truly believe that these all labels are orthogonal to each other, then we can model them as using one-hot embeddings, and then this whole thing, our model reduces to standard conditional random fields or structured support vector machines. But the fun part of the story is when you let these label vectors wander around, and we can let the learning figure out label representations and the weight vectors. So come to my poster, quiz me about the learning. I'll show you some fun experiments and show you how this is a promising direction. Thank you.
Thank you, Vivek. Up next, we have Jose Miguel Hernandez-Lobato presenting predictive entropy search for efficient global optimization of black box functions.
Hello, my name is Miguel, and I'm going to present you this new method for Bayesian optimization, which is called predictive entropy search. Our objective in this is a joint work with Matt Hoffman and Subin, by the way. Our objective in this work is to find the global maximizer x star of an objective function f, which is unknown and can only be accessed through calls to a black box that provides noisy measurements of this function. Our objective is to find this maximizer x star using as few function evaluations as possible. And for this, our strategy is to select at each iteration the next evaluation location to be the one that will shrink the most our uncertainty on the possible values of x star. This is the location that will produce the highest expected reduction in the entropy of the posterior of this global maximizer. The corresponding acquisition function is shown here in equation 1, and working directly with this acquisition function is difficult because it depends on the entropies of this posterior distribution on x star, which is not tractable. And also we have to update this posterior for its input value x at which we want to evaluate the objective. Instead, we can note that this acquisition function is the same as the mutual information between x star and the variable y, which is the noisy measurement returned by the black box. So since the mutual information is a symmetric function, we can then swap the role of these two variables, x star and y, and we obtain this new reformulation of the acquisition function shown in equation 2 that is easier to approximate because it depends on the entropies of predictive distributions that are easier to approximate in practice. Since our new formulation only depends on these entropies of predictive distributions, we call our method predictive entropy search. We perform several comparisons of the accuracy of the approximation performed by predictive entropy search, comparing with a ground truth obtained by rejection sampling shown on the plot on the left. And in the middle, I show the approximation performed by predictive entropy search. And on the right, I show the approximation performed by other existing techniques in the literature that are based on the original formulation of the acquisition function. And we can see that predictive entropy search does a better job in this case on the task of approximating this objective function. Finally, we also perform several experiments where predictive entropy search is used to find the global optimizer of different objective functions, and we obtain results that are better or comparable to those of other techniques. Thanks.
Thank you very much, Jose Miguel. Up next, we have Adarsh Prasad talking about submodular MIPS structure, finding diverse subsets in exponentially large structure item sets.
Hi, this is joint work with Stephanie Jegelka at UC Berkeley and Dhruv Batra at Virginia Tech. And our goal is to predict multiple relevant and diverse structures in exponentially large structured output spaces. To give some motivation, perception domains such as computer vision and natural language processing have to cope up with several ambiguities. These ambiguities may be due to model misspecifications, noise in the training data, or sometimes these ambiguities are just inherent, as it may not be clear what the user really wants. Now, to cope up with these ambiguities, robust prediction methods often hedge their bets. That is, they make multiple relevant predictions, which are then passed on to the user or another system downstream. Now, this task of predicting a diverse subset from a ground set of items is often modeled using the notion of submodular functions. Now, it is known from classical results that the greedy algorithm, which picks the element with the highest marginal gain, achieves near optimal results and works very well in practice. However, here's the catch. In our setting, the ground set itself is exponentially large. For us, each item is a structure. It is a configuration of some base variables. For instance, in image segmentation, the base variables are pixel labels. Each item is a particular labeling or an image segmentation. Since the ground set is itself exponentially large, even a single linear scan for the greedy algorithm is infeasible. Our key contribution is that we draw connections between submodular maximization over exponentially large ground sets and inference in graphical models with higher order potentials. What we basically show is that the marginal gains for some diversity-inducing submodular functions allow structured representations. That is, they can be written in the form of high-order potentials in a factor graph over the base variables. Through this connection, the greedy augmentation step reduces basically to a map inference call to the modified factor graph, thus allowing sublinear time maximization for submodular functions. In our experiments on image segmentation, we show that our algorithm is efficient, and it is also able to construct a set of solutions with a significantly high recall. That is, at least one of the solutions in our set is highly accurate. Thank you.
Thank you very much. Please help me welcome Moritz Hardt, who's going to be talking about the noisy power method, a meta-algorithm with applications.
Yeah, thank you. I want to tell you about the noisy power method and some of its applications. My name is Moritz Hardt, or something like that, and this is joint work with Eric Price from UT Austin. So let me get started. The problem we consider is something you all know and are familiar with. Given a matrix A, you want to compute the top k singular vectors of A. That's, of course, the underlying optimization problem in a number of applications, such as PCA. And there's a wonderful classic method to do it called the power method, where you start with an initial matrix that has k columns, because you're computing k vectors, and sometimes they're chosen at random. And all you do is you repeatedly multiply your matrix A by those k vectors, x sub t, and to keep things nice, you orthonormalize the resulting matrix, okay? And so this gives you a sequence of matrices, and the range of this matrix x sub t converges to the space spanned by the top k singular vectors. So it's known that that happens. How quickly this has been studied for, something like 100 years, but there's still intriguing questions left to be understood, and the one we picked out here is how well does this algorithm converge, or how quickly does it converge in the presence of noise? Okay, so this leads to a meta-algorithm, or a whole family of algorithms that we analyze, called the noisy power method, which is exactly the same as before, except there's now some perturbation, g sub t, that nature deals you, that perturbs your matrix product. Okay, so there's a perturbation that's arbitrary, no assumptions on it are made, and you want to understand how that affects the convergence behavior of this algorithm. What's amazing is that many algorithms in lots of applications can be expressed as an instance of this template algorithm, the noisy power method. For example, alternating least squares for matrix completion can be rewritten as an instance of the noisy power method and can be analyzed this way. And noise in that case corresponds to the missing entries in your matrix that you're trying to fill in. So that's interesting. There are other applications like streaming PCA and privacy-preserving PCA. In the latter, you actively add noise to achieve privacy. And what we show is a general theorem that characterizes the convergence of this algorithm under what conditions it converges. It's rather tight conditions on the initial matrix X0 and G sub t. And just to give you one inequality, if the spectral norm of G sub t is at most epsilon times the eigengap, then the algorithm converges to an epsilon error. So that's essentially the main condition that we get. And we use this to get improvements in all these applications. So come see our poster. Thank you.
Finally, let's welcome Wang, who's going to be talking about two-layer feature reduction for a sparse group Lasso via the composition of convex sets.
Hello, everyone. This is a joint work with Professor Jieping Ye at Arizona State. Sparse group Lasso is a powerful technique to discover sparse patterns in both group level and within group level. However, for large-scale data, it remains challenging to solve the SGL problem, as it has two non-smooth regularizers. Screening has been shown to be very effective in scaling the data and improving the efficiency of many popular sparse models. Essentially, the idea of screening is to quickly identify the zero components in the solution vectors, such that we might have a reduced data matrix and much less variables to compute. The proposed screening method for SGL, which is called TL-free, is based on an in-depth analysis of the dual. However, for the Lagrangian dual, it's not easy to determine the feasibility of a given point. That is, it's hard to tell if the point in the rounded corner cube on the right-hand side is decomposable or not with respect to the ball and cube on the left-hand side. Nevertheless, the differential dual provides an elegant method to find such a decomposition by a shrinkage operator and a projection operator. Then, inspired by the KKT conditions, we can develop the two-layer screening method. The first layer aims to identify the groups with all zero components in the solution vectors by solving a non-convex optimization problem. That is, we need to find the point in the ball that is farthest to its projection onto the cube. And we can get a global optimal for this non-convex problem. The second layer aims to identify the features with zero components in the remaining groups by solving a convex optimization problem. And we also have a closed-form solution. Experiments show that our method is able to identify almost all of the zero components in the solutions. The data has about 0.4 million features that are divided into about 100,000 groups. Without screening, the solver needs about 8.5 hours to solve the SGL problems at 100 parameter values. However, combined with TL-free, it only needs about 6.5 minutes. The framework of TL-free is applicable to a large class of sparse models with multiple regularizers, and the code is available at GitHub. If you are interested, please come to my poster, TOE9. Thank you.
Thank you very much. Please, let's thank our speakers one more time. And that concludes the spotlight session.